Hey guys, Ashton here. I had an amazing opportunity to have a live demonstration of the ENG8 EnergiCell reactor. This is a plasma-based EVO cold fusion reactor. As you will see from these numbers that are shown on the screen in a few minutes, it shows a coefficient of performance of over 3. This is a thermal coefficient of performance. I leave it to everybody else out there to determine what you think of this, but I'm pretty excited by what we see. And I want to go ahead and thank the ENG8 team for doing this demonstration for me. I hope you guys enjoy.
Thanks very much, Ashton, for having us on your show today. We would like to demonstrate to you a plasma low energy nuclear reactor running. So my name's Haslen Back. I've been doing this for about 8 years now. We started off 8 years ago doing on a reactor where we use water to create energy. And the one you're seeing today it's much easier to see. This reactor uses the water moisture in the air to create energy. There's energy all around us, and we specifically use the water molecule as our secret to releasing large amounts of energy. And we can do that either by producing electricity directly or heat directly. And what you'll see today is this reactor producing large amount of photons, and that's effectively light, which converts very, very quickly to heat. The first thing is there's a fan, a high-speed fan, because we need a lot of cooling to go through the plasma to create the plasma effect. And what we're doing is we're creating a vortex. And the beautiful thing about the vortex is it creates an electromagnetic pinch in the middle. And that electromagnetic pinch is where we're getting this very fine linear process happening. And then we're also seeing some arcing, which isn't ideal, but it creates large noise. So everyone's got their ear defenders in just when it starts up. So that's why the noise is actually changing live.
Got it.
And we're just going to restart the machine and the computer, and then we'll boot it up again. And then on the top left-hand side or top right-hand side, whichever way you're viewing this, you'll see this coefficient of performance. So it means that we're calculating the amount of energy and electrical energy is going into the unit usefully. And then we're seeing how many times more energy is coming out of the machine. And in this case, it's thermal energy. So then probably 3 times from the electrical energy going into the heat coming out. And the heat coming out is not like a heat pump. It's like 30, 40 degrees centigrade. It's around 200, 300, or 400 degrees centigrade coming out. So it's very high temperature air. Air can either be used to heat something, to drive a steam turbine, or a turbo generator to self-power the machine. And that's one of our really big things in the next year, is to make sure we've got these machines where we are. So there we are. So you've got the pink, that's lovely pink, running, 3.753 times more power coming out than going in. And in a minute, what I'll ask the guys to do is to shrink the picture, and then I can just talk you through what we're actually doing to be able to calculate that COP, coefficient of performance.
How long can the device run consistently for?
It certainly runs for as long as the guys want to sit by listening to it. We haven't done long longevity trials at the moment with it because it hasn't been our main focus. We've been just trying to get it to operate really stably, to make sure the electrodes don't burn out, to make sure the actual power supply unit doesn't burn out, and to also make sure that make sure the automation process is working well. We've spent the last year working on the automation system, so we're trying to take our hands off the controls and just to make sure it's all working itself. So rather than tuning like an old-fashioned radio to make sure it works, the computer's doing that.
And can you explain once again just what is the physical mechanism that is being used here? Is it some type of similar to the Z-pinch effect that happens with magnetic confined fusion?
Not at all. Well, at least we don't think so. What we've got here is we have created effectively a small pinch, but it's all around the anode.
And the anodes effectively on their surface have got reactive sites where the LNER reactions are happening, as well as in the plasma stream as well. So you see in nature, you see ball lightning, you see fork lightning. It's sort of it's in that area where we're able to extract the excess energy coming out of the machine.
So you're using a vortex then? Is that what you told me?
Yeah, here we've got we've got a high-speed vortex operating here. So what this is doing is this is enabling us to create a pinch. It's also enabling us to cool those anodes. And Gonzalo, just make it much smaller. Can you the picture smaller? Yeah. So what we'll do is we'll make the picture smaller now on the screen. There we are. And on the screen, you've got things like the flow rate, the air going into it. We measure the temperature going in, which is say 33 degrees centigrade going in from the air pump. We've got the outlet temperature, which is showing outlet 3 at 300 degrees centigrade. Where's that heat coming from? That heat's coming from the fusion of the hydrogen nuclei to produce helium. But also, interestingly enough, we're seeing the oxygen in the circuit. We're seeing the oxygen also become carbon. So there's two reactions happening. There's like a fusion reaction happening and a fission reaction happening at the same time. And we can see that by analyzing the gases in the circuit. And what we found is if we use direct current electricity, which we're using for this demonstration, we can basically demonstrate, say, 3 times power out. But if we were demonstrating this using pulse electricity, you could see that 5 or 10 times more energy coming out of the system than actually it is at the moment. But we don't have the pulse generator in this laboratory that I'm in at the moment. And I'll ask the guys to kill it if that's okay, because it's just really, really noisy and shouting.
Sure.
Like, Gonzalo, Anton, just turn it off, please. There we are.
Okay. Wow. Thank you very much. That's incredible. And
Yeah.
I love the data is great here on the COP as well. I think you did a great job explaining in terms of how you're measuring the heat in versus out. Did you say that if you had a pulsed current that you potentially versus just direct current that you could achieve potentially 10 times higher efficiency than what we see there?
Yes, we do. And what we've been doing is as I mentioned earlier, we've been automating the system. Mm-hmm. And so we need it to be very, very tightly controlled, because as soon as we send high amplitude pulses of electricity into the system, then it's releasing loads more energy. And that energy is focused on the electrodes. And those electrodes can become very hot and just literally just like vaporize in front of you. So the presentation isn't spectacular if you've got pulse electricity, because sometimes it doesn't last very long. But with the pulsing, with the automation system, then we can control it very, very accurately. So we can see the temperature of the electrodes. We can then basically fire in bursts of electricity into the system. That basically we can see where the optimum point is on the electrode. We can cut the pulses going in, and we can surf that sweet spot using the computer. Whereas, and also we're embarking in a new stage this year where we are basically implementing AI on the system. So we'll have an AI operator and an AI analyst. And the beauty of that is that I think the Anthropocene Fund in America, we're working with CAN LNER, which is a website. They have an AI enabled library online now. So everyone can go and analyze 100,000 white papers on cold fusion LNER. And what we're doing is basically getting our AI to basically, it's all offline, is to analyze the machine operating, run the experimentation. So we should be able to run experiments, maybe 1,000 times more experiments than you would do manually, analyzing them live, and comparing it to 30 years of white papers to see exactly how we can optimize the system at maximum speed. So I think like AI went from 0 to mass deployment in a decade, and I can't see why LNER can't make that jump, considering it's taken 30 years to get here. But we're now at our company, but also I think 6 other companies at least are at the stage where they're looking for commercial deployment.
So what are you guys trying to achieve? Because I hear a lot about, in terms of research and development, but then there's also, of course, the whole lingering question of commercialization behind the scenes.
Yeah.
So what are your goals?
So what we're trying to do at the moment is get these units working. So we've got like 100 kilowatt power supply blocks. So whether someone wants electricity or whether someone wants heat, and heat can be in the form of hot air or in the form of steam, we can start demonstrating that and testing them at 3 factories around here. So we've got 2 factories that need 38 megawatts, and it's big numbers, 38 megawatts of steam. We've got another 2 factories, the ceramics, and they need 100 megawatts of heating. And then we had a meeting with another big Portuguese company, chemical company, 30 minutes from here. On one site, they need 1 gigawatt of energy. So for us, what we're really focusing on is making sure we've got a very solid, reliable, rugged product that's not pretty and sexy for now, but can be started to really ramp up the deployment and get that into place. So the next 3 to 5 years is doing that. Once we've really got the supply chain running and working well, then we can also license other companies to do the same. So hopefully we'll have a production facility in America in about 3 years, deploying the technology in America for American customers. And the facility we're developing in Portugal is really for developing the European market.
Wow, this is amazing. So what if people are then, interested in this product? People want to know, what do you need in order to go to commercial? Are you raising money for a round of building a device, or where are you at right now on that front?
Yeah, well, basically there's 2 aspects, which one is we're funded by private investors. So we have people investing anywhere from 10 grand to 100 grand is a typical investment in what we do. The more money we raise, the faster we can develop. We have about 35 scientists and engineers in the team, so quite a large overhead of scientists and engineers. We also have within the team the commercial managers and everything else to keep it together. So that's our focus, is basically that 100 kilowatt module in the field operating by the end of the year, and then with the ability to ramp it up. We're also looking for strategic partners, so large companies that need large amounts of energy for their production processes. So whether that's cooking, or whether it's making ceramics, or whether it's making steel or making aluminium, big industrial processes, so we can focus our resources on the big, hugely polluting clients at the moment. And then within 3 to 5 years, we should then be able to start focusing on the more retail, the domestic customer. So people who want to power their houses with low cost energy. And by low cost, I mean the energy from these machines can be 5-10 times cheaper than you're currently paying from oil and gas from the ground or from your solar and wind outside. So it has huge potential. And if you look at examples of Clean Planet in Japan, they've just finished a fundraising round funded by Mitsubishi, Toyota, Nissan. It's big stuff. It's not like niche investors. They're doing well. Brilliant in the States, raised a large amount of money last year. I think it's 20-30 million from a few very wealthy Americans to basically commercialize a smaller reactor, but it's still an LNER reactor. You've got the guys in Canada, Orion Energy. You've got Brilliant Light Power, I think, down in California. So yeah, it's all over. It's Europe, the Far East, America. There's so much activity happening at the moment.
So I guess my next question is more on the science of it, which is, and let's say safety as well. Questions that people are going to have, which is, how is this possible? My analysis would be this must be based on 0 point energy. The idea that space is not empty is how we could be getting over unity kind of reactions like this. So what is your and ENG8's justification, scientific justification for the results that we're seeing?
I think I'll use the example of man used fire for 500,000 to 1 million years before he understood the chemical processes involved. And we were talking to Brian Josephson last year and the year before, who's a Nobel physicist. He got his Nobel Prize when he was, I think, 22 years old. And I asked him, Brian, could you please write us like this a summary of what you think is happening in these machines? And he goes like, no, physicists are always going to be arguing about it. And that's probably going to be the next 20 years or 100 years. So he said, like, just get on and make it work. So our physicists have been in the field for one group, that's the George Egley group, basically for 30 years. Then the other two people have 20 years in this area, the physicists, and they all have different ideas. Mm. So even within one company have different ideas. But what we have found is you either put hydrogen or you put basically water in. That creates you create a very nice stable plasma that's releasing a lot of energy out of the machines. So the machine behind me, device there, which is an EnergiCell, it's this big, and that is currently designed for 70 kilowatts of direct electricity coming out, plus 20 kilowatts of heat. So it's almost 100 kilowatts in something the size of a thermos flask. Now you've obviously got the other bits and pieces to put around it, but the packaging density is similar to a current car engine. So I can just see in the next, like, I don't know, 5 to 10 years, you won't need nearly as much battery out there as you do now. And in fact, you can actually use this process for splitting hydrogen and oxygen very efficiently. So there was the guy in the States who had a car powered by water, I think,
Stanley Meyer.
Stanley Meyer, 1980s. And then sadly, he deceased rather unexpectedly, especially for him. And he basically, he'd almost cracked it, I think, because he had a power car that could power itself. And from the technology we've seen in the lab here, a kilogram of hydrogen contains 33 kilowatt hours of chemical energy inside it. And if you want to produce that by normal electrolysis, you're looking at 50 kilowatt hours. So it's like you're losing money, and losing energy as well as money. We can do it for about between 5 and 10. So let's say 5 when it's nicely stabilized. So you've got 6 times more energy being able to be released than it does to create it in the first place.
Wow.
So if you're, so many people have trucks out there, diesel trucks, and they run on HHO. There's a big thing in America is to get your diesel truck or your car, rather than just running on diesel, they add, say, some HHO to it. It's an additive at the moment, but it makes your car much more efficient. But a diesel engine or a petrol engine can burn it. What I see in the next 5 to 10 years is there'll be loads of people with kits going into their cars. So rather than converting over to LPG or putting some HHO in their car, they'll be able to run their car on hydrogen, electrolyzed, ionized hydrogen oxygen. The beauty of that is you burn it in the engine, converts to water. You don't add the air, so it's disconnected. It's a closed circuit. So your engine effectively is burning HHO. It goes through the radiator, which is effectively a condenser at the front of the engine. It basically goes back through an electrolyzer, and it just keeps going round and around and around. And then you don't have any fueling costs for your car. You've got basically all the infrastructure in your car ready, or your truck, or your freight train, or your generator set out on the ranch.
Well, so let me just recap what you just said, because I think this is the most vital part for anyone to actually understand the exact numbers of what we're dealing with here. Is that you said conventionally it would require 50 kilowatts of energy to produce 1 kilogram of hydrogen from splitting water. But potentially using this process, it could be done 10 times cheaper than that. And that's significant because that means you could do it for 5 kilowatts and you can produce from 1 kilogram 33 kilowatts. So you're getting almost 6.5 times the amount of energy out than what you would have been getting in this process of breaking hydrogen and oxygen apart and then putting it back together, right? So you'd have one area where you're breaking it apart, comes back together over here, break it apart, and you just keep doing that process. And since the overall process produces more energy, it's just perpetual.
Yeah, and to explain that is possibly the American guy, Randall Mills, with his company, Brilliant Light Power. He's done decades of research on this aspect, and he's not seeing transmutation as you would do in a normal LNER reactor. He's seeing the hydrogen state going to a super low energy state and releasing a large amount of photons in this process. Wow. So we are assuming, or our conjecture is that as the oxygen and hydrogen are going around, it's the energy state of the electrons that are basically going down and down further. And then at Brilliant Light Power, they commissioned Delft University to do a study of what happens to this hydrogen oxygen. Is it safe, or hydrogen, is it safe? And they showed that when you expose this super low state hydrogen to sunlight, actually the electrons absorb the photons, and the hydrogen atom returns to its normal energy states. Wow. So it's almost like this eternal energy system, because you're not burning anything, you're not consuming anything other than converting photons to electrons, electrons to photons.
It's almost like our whole universe is one big energy system, almost like the water table on Earth, you know?
Yeah.
So, well, last question or kind of topic is the risk, the safety aspect of this. You know, I think that it's similar to nuclear power, where it was like the 90s when everyone started freaking out about nuclear power. We had a couple of reactor meltdowns, and then so we decided, at least the West, maybe in Europe, you guys are a little different, but in America, like, we decided to shut down all of it. And now there's a push to go back to it. So I have similar questions about fusion power in this. I mean, if I have a little fusion pack on me, is that thing going to explode in my scooter or on my bike? Or, I mean, what's the danger here?
Well, the interesting thing between classical fusion and fission reactions is they're producing alpha, beta, gamma particles, basically, so neutrons, and that they are very high energy. They're very dangerous to DNA, so they create illnesses. These reactions, they generally all create something called a condensed plasmoid. And a condensed plasmoid is a collection of billions and trillions, 10 to the 26 plus electrons. And this huge negative potential basically pulls apart the electron shield of any atoms that come in contact with it. And they enable the nuclei to just fuse as you would do in a chemical process, but it's a nuclear process. Now, this huge negative force, for some reason, allows photons and electrons to escape, but it doesn't allow high energy particles as neutrons, alpha, beta, gamma radiation doesn't come out. So when we've had the Technical Electrical Institute of Portugal here with all their detectors, they're seeing nothing above background radiation levels. So one of the things what we are very concerned about, though, is what is the effect of these reactors on plants and animals. Yeah. So we're going to be doing in vitro testing in the next 18 months to make sure that we're not seeing any strange effects on in vitro. Then we're going to be growing plants with them next to them. Now, what we've seen from a number of companies is when you grow plants near plasma at the right frequency, it can double the growth rate. You've seen that.
I had that. I was literally going to ask. That's why I was smiling. Is that, first of all, I want to thank you for actually researching these things. I think that I know I have a lot of followers who are concerned about, like, what are the dangers of this stuff, and we don't really trust the government to research scientific stuff. So what you said there's no radiation, which is like, why? And then you kind of are like, why is this phenomenon that we see photons get emitted, but we're not seeing other particles get emitted?
Yeah.
And then I was going to say, yes, you should check to see if it makes plants grow, because there's this idea out there, at least, that plasma can stimulate plant growth. And heck, you might just figure out that you find a whole new commercial purpose for this so I think that would be interesting to research, and I definitely would want to see what the results are on that.
So this technology that's behind me, if we get it really right, and we can produce energy, happy Christmas. But if it's a device that's in your home or your car, and it's actually doing a benefit from you, it's not like carrying a cell phone around that's frying your DNA in your hand because of the high amplitude energy coming out of a 5G. We want to make sure these devices are super safe and actually beneficial for you and the whole environment around us.
And then I guess my last question's a bigger one. It's more of a societal, political one. Is that, we're pretty much talking about, in my opinion here, free energy. And we're talking about efficiency, not just producing something from nothing, but basically being able to get efficiency where you can accumulate unlimited amounts of energy. Anytime that comes up, you have to think of national security. What are the bad guys going to do with this? and I worry about the negative aspects of this, somebody making a bomb or something like that. So what are your thoughts in general about how we would prevent something like that happening with any form of advanced energy, but in this case, you know, fusion, cold fusion?
Yeah, I think cold fusion, in terms of its military things, I think the cold fusion cat's out the bag in the military anyway. I think they've used it for a number of years. I think depleted uranium warheads, when they actually impact on tanks, there's not just the kinetic energy involved. There's a whole load of LNER effects around this, and that can be seen anywhere where depleted uranium is being used, from the Gaza Strip to Kuwait to Iraq, Afghanistan. You can suddenly see a whole myriad of different isotopes where these depleted uranium warheads have been used. So that's a sort of an LNER effect from the military. Rumor has it there's a submarine out there which is actually cold fusion powered. Rumor has it there's also some very fast missiles out there that are cold fusion powered at the moment, or cold fusion enhanced out there. So we basically have devices here that we work on, that I guess, if you stretch the imagination, you could probably put them in a tank, but I think that the whole military industrial complex has probably got the tech anyway. We try and focus on making sure it's being used for peaceful applications. When we roll it out, we'll try and educate our customers that, running around the Amazon with a nuclear powered chainsaw isn't the best thing for the environment.
Yeah.
Or a tractor, the supercharged tractor that can just tear up, when you get low cost energy, they say energy should be matched with consciousness. So
yeah.
we hopefully we will have the ability to deploy it as responsibly, as humanly as we possibly can, and also it'll have huge effects. We imagine India, 40% of households are living and burning cow dung at the moment, and basically have huge respiratory problems. If they had a device, an LNER device about that size in their house, they wouldn't need to be burning cow dung anymore. They could actually just have electricity 24/7. They could have heating. They could cook off the power, everything. It would completely change the health of billions of people on the planet at the moment.
Yeah, and I think that's the big thing, is that we have to be conscious about the capability of this technology. It's real.
Yeah.
And it can change everything about our civilization. You just gave us some really great examples there about how it can help the third world, how it can help the first world.
Yeah.
But there are risks that we can't just ignore. So I'm glad that you're conscious to those. I'm glad that you're conscious to the safety aspects of what it might do to people and plants as well. And thank you very much for this interview and this discussion.
Thank you very much.
I've learned quite a bit more, actually, that you uncovered here for me, and understanding on how this science actually operates. So thank you guys, and thank you all.
Yeah,
ENG8.
and we have quite a open lab, by the way. So if you ever want to come over and check it out, do. We have loads of our investors often come over, and the fan club, basically checking out the machine and seeing what we're doing. So if you've got anyone that wants to come have a look, we're here.
I plan to take you up on that in the future. Thank you.
Cool. Thanks, Ashton. Have a lovely afternoon.